Thank you very much. It is my pleasure to talk about such nice conference. I was going to visit Bangalore, but some administrative work came in and I couldn't. So it's a reality. So I hope I have next chance. Yeah. Now, yeah. Can you see the file?
Yes, we can see it.
Okay. I think internet connection maybe not so good, so sorry about it. I will talk about Rubin's conjecture on local units in the anticyclotomic tower at inert primes. This is joint work with Ashay, Burungale, and K-Ota, chairman. So these two people are in Bangalore now, but I give a talk from Japan. So first introduction. In my talk, let P be a prime number greater than 5. And in this introduction, the elliptic curve defined over Q rational and good at P and CM by imaginary quadratic field K. If P splits in K, then it is well known that E has good ordinary deduction over P, and USR theory is really well developed. For example, Kurzweil's Rubin, it provides an ideal model of USR theory in this case. But if P is inert in K, the situation is different. In this case, it has super singular reduction at P, and USR theory is not so is satisfactory only for cyclotomic deformation. For example, anticyclotomic deformation and high to intake deformation related to such division tower is not satisfactory. Yeah, of course there are important works like Berger, Andrea Teopita, maybe Schneider, Benjamin for Rubin tower. We was a theory for Rubin deformation, but yeah, it is still developing subject. Today, I talk. My assumption is that P is inert, and K infinity over K is anticyclotomic G extension, which is a unique GP extension of K, which is Galois over Q, and whose Galois group is dihedral over Q. And then another characterization is K infinity is unique GP extension lives in ring class fields tower. And in this setting, there is a special phenomenon. I explain it now. Let phi be Heck character associated with E, and suppose chi is anticyclotomic finite character, order p to the power n, non-trivial. Then Sorry, I'm using old notes, so I fixed this. So sorry. Yeah. Maybe I will change. No, this is old. Oh, wow. Sorry. Old. This one may be better. Yeah. Yeah. So, so the L function is self-dual, and so the root number is plus minus 1, and satisfying this formula. Yeah. So usually in USA theory, root number is usually constant, but in this setting, if you move chi to the power varying chi, then root number changing depending on the parity of n. So it's a little bit special phenomenon in this setting. And in particular, if n satisfies, so if n is equal to the parity of the root number of phi, then root number is minus 1, so L value, the L value vanishes. So many zeros. There are many zeros in the direction of anticyclotomic, in the anticyclotomic direction. So yeah, so there are many zeros. So we expect rational points by BST conjecture. So now we state our first main theorem. So it describes the variation of model value rank in the anticyclotomic tower. So consider the model chi part of the model value rank of the nth layer is 2 or 0, depending on the parity of n for sufficiently large n. So in particular, for sufficiently large n, the difference between the model value rank on the nth layer and n-1 layer is like this. So epsilon n is 0 or 2, and epsilon n is 2 if and only if the parity of n coincides with the parity of W phi. And yeah, essentially, this so far this is proved by Ralph Greenberg in his unpublished paper. We don't know his proof, but I think our proof also is same as him. And the new part, our contribution is that first, if P does not divide the algebraic part of the L value, so in particular, L value is not 0, so the number should be 1. And then in this case, we saw this holds for all n. This is a new contribution. And the next number 2. So this is analytic rank 0 case. So the second is analytic rank 1 case. So we assume analytic rank 1. And so the root number is -1. And we also assume global model value group generates local model value group. Under such assumption, and now we assume P does not divide the special value of the leading term of L value. So the derivative of L value in this case. Then we also have that this holds for all n. Yeah. So in this setting, we have, but we can completely control the behavior of rank along the anticyclotomic tower. I remark that for sufficiently large, it means so this comes from the Rohrich result. Yeah, by Rohrich, for sufficiently large n, the analytic rank of L value is determined by parity, root number 1 or 0. So depending on this, we have such formula. By using Gross-Zagier formula. And we compare our result with cyclotomic case. For example, cyclotomic case, under this assumption, the model value rank of in the GP cyclotomic GP tower is bounded. So this is the result of Kato-Rohrich, well-known result by Kato-Rohrich. Bounded, sorry. If P does not divide L value, so it is finite, always finite. So model value rank is always 0 in this assumption. So we also our result is in some sense analog of this result. Now, I want to explain the Iwasawa theory behind this theorem. So in the late 80s, Carl Rubin developed certain Iwasawa theory, which explains this phenomenon. Under so-called Rubin's conjecture, which is the main topic of this talk. And so this is an origin of the plus-minus Iwasawa theory. I studied plus-minus theory for cyclotomic deformation, but at that time, I didn't know Rubin's work. But after that, I learned Rubin had an idea of plus-minus theory already in this setting. But unfortunately, in his setting, so Rubin's conjecture is not solved. So plus-minus theory is not developed. It was not developed. And so now I explain Rubin's conjecture and our proof of the conjecture. So Rubin's conjecture is local. So for local fields, it's not a global conjecture. This is important point. So I switch to local notations. Let psi be the unramified quadratic field extension of QP, and so for application, of course, we take psi as the p-adic completion of K in the introduction. And we denote O the integer ring of psi. And now psi infinity over psi is a local anticyclotomic GP extension. Yeah. So in the setting of introduction, so the class number of K is 1 because E is defined over Q. In this setting, yeah, so global anticyclotomic extension. It's essentially so global one and local one coincides naturally. Anyway, yeah, Rubin's conjecture is local, so we consider local anticyclotomic GP extension, and let lambda be Iwasawa with coefficient O, and we fix the Rubin Tate formal group over O height 2 with parameter minus P. Note that yeah, the formal group of E in the introduction is isomorphic to F over O. More generally, for any elliptic curve A defined over QP with AP equals 0, the formal group of A is isomorphic to F. So Rubin's conjecture, our theory can be also applied for such a not for the non-CM so any elliptic curve or super singular elliptic curve over QP with AP equals 0. So yeah, in some point the one of my key point is to forget complex multiplication. So yeah, so it is important, yeah, to consider Rubin Tate formal group instead of CM elliptic. And in our proof, yeah, we choose many good A's such that whose formal group is F. So CM1 on CM. So we fix formal group F and later varying many elliptic curve A isomorphic, whose formal group is isomorphic to F. Yeah, now we consider the Iwasawa cohomology, local Iwasawa cohomology H1T, which is the inverse limit of the Galois cohomology on the nth layer. Yeah, here T is yeah. So T is TPF. T1 is Tate twist, and tensor minus 1 means O dual of T of T1. And Iwasawa algebra canonically acts on H1 of T. So this is a space of local unit in the anticyclotomic extensions by Kuhn's theory. Yeah, in my talk, I put the word local unit, but actually local unit will not appear in my talk, and instead, yeah, this Iwasawa cohomology appears. But actually, yeah, H1T can be described in terms of local unit. Now, we consider anticyclotomic characters. So let X be the set of anticyclotomic character of finite order. And we divide x to x plus and x minus. X plus is the characters whose order is odd power of p. X minus is characters whose order is odd power of p. So it's a little bit so here plus and odd. So it's a little bit seems strange, but actually conductor of chi is p even. So conductor of chi and order of chi is different by one. So if we use conductor instead of order, yeah, plus means even. So it's a matter of normalization. And following Rubin, we define lambda submodule H1 plus minus of H1 as a cohomology such that V is in H1 plus for if and only if V is killed by dual exponential chi part of dual exponential where chi is minus, so chi minus x belong to chi minus. So V is killed by all character killed by dual exponential. So chi part of chi belong to x minus. Yeah. It seems a little bit to consider such subgroups, but maybe you should note that if conductor of chi is so if V is killed by dual exponent chi part of the dual exponential, then so the kernel of dual exponential is H1F, so rational point. So VM. So VM belong to the rational point of formal chi part of the rational point of formal group by comma map. So usually in Iwasawa theory, we consider the Iwasawa cohomology H1F. H1F is the limit of H1F, and so H1F is the element which is killed by all dual exponential map. But H1 plus minus we consider elements V which is killed by dual exponential for chi with certain parity. Yeah, you may remind remind Greenberg's our theorem, Greenberg's and our theorem in the introduction. Yeah, model behavior is something like this. So we expect local analog as a local analog. We consider such spaces. Yeah, so we belong to model value rational point, set of rational points depending on parity. And Rubin shows that this is special subgroup is free lambda module of rank 1. And he conjectured that this is Rubin's conjecture. Iwasawa cohomology is decomposed into H1 plus and H1 minus. And our main theorem is that Rubin conjecture is true. So I now explain applications of Rubin's conjecture. First, using H1 plus minus, so-called the plus minus Iwasawa theory can be developed for A with formal group F, and in the anticyclotomic GP extension to Inert P. Actually, Agbura Howard already developed plus minus Iwasawa theory for CM elliptic curve E introduction in the introduction with conjecture. And so I want to remark that we can apply our theory to non-CM elliptic curves to if A has formal group isomorphic to F. For example, if A is defined over QP with AP equals 0. And we can also, by using the technique for proving Rubin conjecture, we can obtain BDP type formula for Rubin's p-adic, which is p-adic L function suitable in this setting. And we also have application to Kato's local conjecture in our setting. This is the topic of Ota's talk today. And we also give some asymptotic formula for the p-adic variation of L value share formula. So actually, Rubin's conjecture is fundamental, and can deduce many things from Rubin's conjecture. Now I explain the idea about proof. Idea is to construct an element of H1 plus minus, which generates H1 over H1 minus plus. So we need some little algebra, but essentially by something like Nakayama's lemma. If we have good generator of this module, then we can prove Rubin's conjecture. And so we construct a good element in H1 plus and H1 minus. For H1 plus, we use elliptic units to construct the desired generator. And for H1 minus, we use formal CM points. This is a new idea, our new idea, to construct the generator. First, I explain plus case. Now we take elliptic curve A, CM by imaginary field, quadratic field K. K is not necessarily it's a K in the introduction. Maybe I should write F. I should write H is Hilbert class field of H. So we take elliptic curve A, and we remark that that since P inert in F by our assumption, P splits completely in H. So the completion of the Hill level to class field at the place over P is unramified quadratic extension beside the bottom field psi. This is an important point. And now we consider a system of elliptic units, theta A, which, so by definition, by Kumma map, it lives in disk homology group. So this is global Galopp homology group, P division tower. And by localization and projection to the anticyclotomic direction, actually this distributes we think theta A as an element of our H1. And as I remarked, the completion of H is psi. So we don't need the trace operator to K. Actually, so the localization directly defines element of H1. This is an important point because if we take trace, then something may happen. So it vanishes, for example, vanishes or some like Mazur's conjecture, such trace is sometimes harmful. So in this case, we don't need to take trace. And the characterization is that elliptic curve dual exponential theta A is L value by Wiles reciprocity law. And so suppose that the root number of phi A is epsilon. Then, as I remarked in the introduction, root number of phi A chi is -1 to the power n plus 1 times epsilon. So this means that so if the sign, if certain parities, this L value vanishes. So theta A belongs to H1 epsilon. So our H1, H1, the definition of H1 plus minus is element killed by dual exponential map force. Yes.
We cannot see your screen now.
Oh, why? Can you see?
Yeah, we can see your screen. Yeah, thank you.
So when did it stop? So where should I start? Anyway, so if the root number is -1, then this vanishes. So theta A is killed by dual exponential map for characters of certain parities. So from this fact, yeah, we see that theta A belong to H1 epsilon. So we have at least good element in H1 epsilon. So, now, so if but we want to show this generates this space. For this, we need to find elliptic curve AA such that the L value is P indivisible. P does not divide the L value, so p-adic unit. Yeah, for this, yeah, root number must be plus 1. So we H1 theta A, we can construct theta A belong to H1 minus 2, but yeah, then L value vanishes, so it not suit for our purpose. So we now consider A belong, which so whose elliptic units belong to H1 plus. And if we had such P indivisibility fact, yeah, we can show theta A is desired desired generator. Yeah, actually, yeah, Rubin. This is Rubin's idea, and Rubin showed that H1 plus is free of rank 1 by using such theta A without this condition. Yeah. In addition, yeah, if we have this, yeah, it suits proving Rubin's conjecture. And so actually, so the problem is that it is very difficult to find A having this property. Yeah, at least when Rubin wrote his paper, yeah, we didn't have any general result like this. But now we have finished result. So our idea is to the same as Rubin, but reduce to finish the result for indivisibility of L value. By finish, there is a finite ring class character of conductor L different from P, such that L value of phi eta does not divide, PP does not divide the L value. Since P splits completely in the ring class field, so localization ring class field is again psi. So without taking trace, we can define elliptic unit in H1 plus such that yeah, whose dual exponential map is L value, which is not P divisible. So this is the desired element to prove Rubin's conjecture. Now I explain minus case. In this case, yeah, such L value never be a p-adic unit. Yeah. Yeah, for example, bottom case root number is -1, so So if chi is 1, this vanishes, so never p-adic unit. And we can consider chi of higher conductor, higher peak ramified character, but it is really hard to control p-adic variation of such value for ramified character. We don't know finished result so ramified character. Actually, yeah, for ramified chi, this value is never p-adic unit. And in fact, by using Rubin's conjecture, we can control the p-adic variation of such value. So actually, almost so to show Rubin's conjecture is in some sense equivalent to show equivalent to control the p-adic variation of such value. But now, so we have two possibilities, two choices. So we calculate the p-adic variation for ramified character, generalized finis, or we use another method. So we chose the latter. Yeah. So -1 case, we don't use L value, elliptic unit. But the sign is -1. So we may expect some rational points by PSD philosophy. And so instead of L value, certain rational point will play an important role. For example, Hida points. This is also Rubin's idea. Rubin shows that suppose that there are good local points of formal group in the anticyclotomic tower, satisfying the two conditions. One is some certain trace compatibility. This relation is common in the plus-minus theory. Coming from the factor AP equals 0. So this is not an error. This is n+1 and this is n-1. This is not an error. And the second condition is subtle. The bottom C0 cannot be is not divisible by P. If we had such good local points, we can show, at least Rubin showed that, it becomes, we can construct the desired generator of H1 minus. And hard condition is, of course, 2. Without 2, Rubin constructed such points satisfying only one, and it implies by using the system, Rubin showed that H1 minus is free of rank 1. But for Rubin's conjecture, we really need the system satisfying 2, the condition 2. The idea of the construction of such local points is as follows. For example, we take elliptic curve E prime with AP equal 0 defined over Q, and take modular parameterization. And let F be another imaginary quadratic field where P is inert, and consider Hida point of conductor P to the power N, and we consider the image its Higna point. Then such Higna system of Higna points satisfies the relation one. Yeah, this is well known. And you should note that certain PP, so CN belong to the formal group, and its formal group is isomorphic to F. So by using Higna points, we can construct points here of formal group. Yeah, it's a little bit strange. Yeah, to prove local things, we use very global object modular parameterization Higna points. So, but it is very hard to show that for such system, she satisfies two. Yeah, because we used a lot of global things, modular parameterization and Higna points. So it is a hard problem to determine Higna point is divisible by P or not in the local model way. So there are many choices of E prime and F, but we actually this is Rubin's idea, but yeah, we think it is hard to get systems satisfying too by using Higna points. Yeah, actually, yeah. So there should be also another method to construct such local points. It is essentially pair-and-Lie theory. Pair-and-Lie theory. Yeah, pair-and-Lie theory is equivalent to construct such local points by p-adic theory. But as I said before, pair-and-Lie theory is not available for this setting. Yeah, though there are several developments for Rubin data tower. Yeah, so the obstruction is yeah, we don't have general theory, general local theory to construct such points. Yeah, in the cyclotomic setting, yeah, I used pair-and-Lie theory, Honda's theory to construct such points. Yeah, our idea is to use formal CM points instead of Higna points. Formal CM points, I mean that yeah, it is a point of modular curve, and A may not have CM, but A hat, so the formal group has in some sense CM. Yeah, it is bigger than GP. For example, any elliptic curve A defined over QP with AP equals 0 or P super singular with super singular in this setting has formal CM. So CM elliptic curve CM points are in some discrete, but formal CM points dense. Many there are many in the modular curve. Our idea is to use formal CM points instead of true CM points. So we take an elliptic curve A may not be CM, such that whose formal group is isomorphic to F. Then by using Gross's canonical rift, theory of Gross's canonical rift, we can construct a tower of a system of isogene like this. Yes, such that AN has formal CM, and whose endomorphism ring is GP plus P to the power NO. Ring class field of conductor P to the power N. So this is ring class field of conductor P to the power N is almost equal to nth layer of anticyclotomic extension. Nth layer of anticyclotomic extension. So yeah, I recall the construction a little bit. So F is Rubin Tate. So the Tate module is free of rank 1 O module. So we take generator E, and by using such some module, we have cyclic subgroup of order P to the power N in A, and we divide A by Cn, and this is N, and the graph shows that yeah, this is in fact satisfied. This in fact satisfies these things, and we have sequence of isogenes, and let Xn be a formal CM point associated to An with appropriate level structure, and take a modular parameterization again, and put Cn is the image of Xn. Maybe I should multiply P to the power N to the square. Then yeah, for appropriate choice of A formal CM curve, we can show C0 Cn satisfies the condition 2. Yeah. Yeah. Maybe you look this picture. Yeah, this is modular curve. This is E, and we take modular parameterization, and yeah, by choosing so pi is étale for almost all points. So ramification point is finite. So we can choose appropriate supersingular point. Then the residue disk at the origin of E, and the residue disk at supersingular disk is isomorphic. And yeah, and P power P so P hat is here, and the inverse image is here. So, but this is isomorphic. So we choose some point around here, and by the isomorphism we choose point here, and and almost all points has formal CM. So we get appropriate elliptic curve A. By construction, it satisfies this. This is our idea. So formal CM points are really easy to handle compared with the two CM points. This is our idea. Now I have 5 minutes, so I explain Rubin's p-adic function and BDP formula. Yeah, let E be an elliptic CM elliptic curve in the introduction, and theta is the elliptic unit for theta E belong to H1 epsilon, where epsilon is the parity of phi E. And we fix the generator V of H1 epsilon and write theta E like this. So L function, p-adic L function is ratio of local units and elliptic units. So it's classical. Local usually p-adic L function is local unit modulo zeta element. So we define Rubin's p-adic L function by this formula. Then it has the following interpolation property. So for chi with parity epsilon, LP, chi of LP related to a complex L value. The fundamental question is BDP type question is that what is the value of LP at chi with parity minus epsilon. So it is out. So chi belong to the range of interpolation. So outside the range of interpolation. BDP is now popular, but the original question is, of course, Rubin in this setting. And the natural expression is like p-adic P grosses are given by BDP. This value should be related to a rational point of elliptic curve. Now I state our theorem. First, we consider the bottom case. So suppose epsilon is -1, root number is -1. So the trivial character does not belong to the interpolation range. Then there is a rational point P, global rational point P, satisfying the following properties. The value of p-adic L function at the trivial character is written in this way. CP is rational number, almost rational number. And P is formal log P, and V0, by definition, V0 is killed by dual exponential, since V belongs to H1 minus. So V0 defines element of formal group. So we take log of, we can take log of V0. And so ratio of local generator and global points appears. And second, P is torsion if and only if the analytic rank is equal to 1. And if the analytic rank is 1, then this CP is described by the complex L value, the derivative of the complex L value. So it is really something like p-adic variance on conjecture value in this setting. The second theorem is for general chi with higher conductor outside the interpolation range. In this case, our theorem is not so satisfactory. We consider the elliptic unit, chi part of the elliptic unit, then almost by definition, it belongs to Selma group. And the value of p-adic L function is described by the log of theta E chi. And if the analytic rank is 1, theta E chi generates model wave group. But this model Bell group is tensor over QP, not global field. So here, so in theorem 1, P is real global points, but theta E chi, there is tensor by p-adic field. So it's something like Kato class or Rubin class. So less satisfactory compared with theorem 1. I stop here. Thank you very much.
Thank you very much. Let's thank the speaker. Are there any questions or comments?
You mentioned as an application close to the about the growth of texture for Elliptic group. So what?
Sorry, I can't hear.
The growth of texture.
Growth. Yeah.
What can you say exactly?
Yeah, it's so in the cyclotomic setting. Yeah, Kurihara and I, many people prove the asymptotic formula of the SHA. That's, it's hard to read. So in the ordinary setting, as you know, there is Iwasawa's formula, like what I know, something like this. And in the super singular setting, this part becomes really complicated, but we can write down. We have similar formula.
Okay, like Kurihara's work.
Like Kurihara's, it's formula is not exactly the same, but it's something like that. Yeah, it's hard to write down. Yeah.
Oh, okay, then doesn't matter. Thank you.
Yeah.
Any other question or comments?
Hi. Yeah. So in the first case, you mentioned this Finnish work. So can you really construct some? So can you really construct some particular elliptic curve with those required properties?
You mean plus case?
Yeah, plus case.
Plus case. No, it's
here.
Yeah, is I think any elliptic curve is okay. Yeah, but eta is given abstractly. Yeah, so I think we can just say there is eta, some eta. Yeah, and I think eta is not explicit.
And in the next case also, like you gave this pictorial explanation. So here also you explicitly construct some elliptic curve also.
Yeah, in this case, I think almost any elliptic curve is okay. Maybe even Higuna points is usually okay. So, but fact is that it is difficult to prove P indivisibility, but numerically, almost all elliptic curve satisfies, desired property. Yeah.
So, but then finally, like when you construct these rational points in the main theorem, so then get some relationship between like normal Higner points in this setup, like in the rank.
It's a good question. Yeah, it's a good question. Yeah, in this set, so P is in some sense, P is given by Higner point, but it is not canonical. Yeah, we use the Higner point to construct P, but so Higner point is not associated to the imaginary quadratic field CM field of E. Actually, so E does not satisfy Higner hypothesis. So we don't have canonical Higner point in this setting. Instead, we take auxiliary imaginary quadratic field F, which is not related to E, but satisfies Higner condition. And we consider Higner point associated to this auxiliary F. And P is essentially the image of ZF. So, yeah, this P is not canonical. The formula is canonical. Yeah, if we choose, yeah,
Okay. Yeah.
another P, then CP changes. So, yeah.
Okay, thanks.